Okay, class, welcome back. We are talking about cellular models or CW models for spaces today. This is kind of a an interpolation somewhere in between a CW model for X and just the underlying subcomplex A, which is a CW complex. And we'll try to tease apart what exactly that means. So we're going to fix a subcomplex of X, which is, sorry, X is a space, A is a CW complex, non-empty, living inside of X. And so last time we talked about adding, we already know how to add cells onto A to end up with something that is homotopy equivalent, weakly equivalent to X, pi star isomorphism equivalent to X, without changing A. So we know we can add on a bunch of cells. And today we're going to kind of build on that, add some flexibility. So the definition is that an n-connected CW model for X, comma A is an n-connected CW pair, which we'll unpack in a second in case you've forgotten, Z, comma A, and a map of pairs ZA to XA, so this is like a map from Z to X, such that the restriction on A is the identity, and it's an isomorphism for I bigger than n, and an injection on pi n. So let's look at a couple examples on what that would mean. So let's unpack the first thing. So here's the whole definition. So first, recall that n-connected pair Z, comma A, so A is the same A in both cases, but here Z is CW, is the same as saying that the inclusion from A to Z induces an isomorphism in degrees below n and a surjection in degree n. So, and we can see that from the log x sequence. So that means A into Z is a pi I iso for I less than n and a pi n surjection. And so this is coming from the log x sequence of the pair because I've got pi I Z A. So these are the groups which by n connected are trivial in degrees up to and including n. And then the connecting map goes to pi I of A, I minus 1, pi I minus 1 of Z, etc. And coming from over here, we've got pi I of Z, pi I of A. So here's the long x sequence associated to the pair in homotopy groups. So if this is 0, and presumably as we keep extending to the right, you know what, let's do this in colors. So as we go to the right, the next guy is pi I minus 1, Z, A. So if I is less than or equal to n, the picture we end up with is that this is trivial. So I'm going to write trivial group is 0, and then this has to be an isomorphism of groups, and this, not that map, this map is necessarily a surjection, and it might be an isomorphism if I is strictly less than n, but then it's actually guaranteed to be a surjection only in degree n, or that's all we can guarantee. So recall that this is true. And let's look at a couple examples. So the thing I want to do is try to unpack what this means when n is small and when n is large. So the smallest a CW pair can be is 1 connected because pi 1 is a set. So let's start with that example. So let's say n equals 1. So if we're looking at a 1 connected model, that means that all we know is that pi 1 of Z is surjected onto by pi 1 of A. And that's it. And A is non-empty, so yeah, we know that the base point of A lives in the base point component of Z, and then we would know that we have this surjection in pi 1. And the rest of the requirements up here for this model, F, tell us that the map F from Z, comma A to X, comma A, induces pi star isomorphisms from pi star of Z to pi, let's use an I here, pi I of Z to pi I of X for all, this is an isomorphism for all I bigger than 1, and it's a surjection, or sorry, injection in I equals 1. So we have sort of this sequence of spaces, right? You should think of this as A is living inside of both Z and A is living inside of X, and we have this map F, and F is now making Z look like, in its higher homotopy groups, look like X. So you could probably extend this definition of n-connected pair to n equals 0 as well, and just require, and all that says is that pi is that A's base point, or it'll be a surjection on pi 0, so that would mean that A's connected components surject onto Z's connected components. So in that case, you would end up with an isomorphism on all higher homotopy groups in high degrees. So let's just point this out. N equals 0. You'd end up with pi 0a surjecting onto pi 0 of Z. And then this would tell you that F star is an isomorphism. Pi I Z, pi I X for all I bigger than 0. So in all higher degrees. So Z in this case, when n is very low, looks predominantly like X, like it has all the high homotopy group information of X. However, if n goes to infinity, we kind of go the other way. So again, so if n equals like infinity or large, then the inclusion of A into Z is a weak equivalence. Therefore, homotopy equivalence. And the map from Z to A, or sorry, the map F that we're given from Z to X is an isomorphism in infinitely high degrees. So is just a map. There's no conclusions about it. So in this case, what we have is like A living inside of Z, but weakly equivalent, and then we have this map F to X, whereas above what we had was A living inside of Z, which was a CW replacement, very close to. In the 0 case, it looks like this. If n equals 0 and A, X, both path connected. So we get rid of the base point issues. So we're kind of interpolating between these two different cases. And I'm using reminder, this means weak equivalence, i.e. pi star isomorphism, not homotopy equivalence. So, okay. So the basic proposition is, for such pairs, these exist. So n-connected models, ZA exist for all n greater than or equal to 0. And in fact, it can be constructed only with cells, new cells in degrees bigger than or equal to n. Strictly bigger than n. So they can be constructed from A. So you should think that we're taking A inside of X, which is already weakly equivalent to itself, and we're going to just start adding cells only in degrees bigger than n to adjust the higher homotopy groups to look like X is. And we can do this by adding on new stuff that surgex onto the homotopy groups for X, and then killing any additional relations that are in the kernel to get an equivalence going up. So the proof is going to be just that one sentence. Add cells to A inductively starting at degree n plus 1 to get a map Z to X with the desired properties. Sometimes these proofs, I know you've now seen a couple of them, they are sometimes described as like designer homotopy group spaces, designer spaces for homotopy theorists. We're basically constructing some space that has exactly the right homotopy groups to some set of requirements that we are writing down. And provided you can do your inductions going up, and you know that adding additional cells is only going to alter things 1 degree down, you can kind of like customize your cells to be whatever you want, and customize this map to be whatever you want. So this is essentially all that constructing a CW approximation to X that looks like A up to degree n, and then looks like X above degree n looks like, which is what Z is. So the main results about these models is they give us, they're the level of generalization we can prove about uniqueness of models. So given 2 different models for different spaces, so I've got ZA for XA and Z prime A prime for X prime A prime. The first one's n connected and the second one's n prime connected. And a map of pairs between X and X prime, or XA and X prime A prime. If n, so if the connectivity of this first model is bigger than the connectivity of the second model, and remember that higher connectivity means Z looks more like A, greater than, and notice this is greater than or equal to, which is fantastic, then we can find a lift, I see a mistake, H from Z to Z prime, which is right there, such that on A, H is just doing G, and it gives us this commuting square up to homotopy relative A. So this square doesn't actually have to commute, but what we're getting is a homotopy from f prime h to gf relative whatever is happening on A. So we can do this homotopy, on this new space that we constructed by adding cells, we can extend G, or G restricted to A, to a new map H, and we can do such that it is homotopic to G relative these replacements, which is already pretty great. But now the really awesome thing is H is unique up to homotopy relative A. So coming up with, so I didn't write it as unique because it's only unique up to homotopy, but you could think of this as homotopy unique. Rel A. And this is really strong. Uniqueness is super strong. So just to be clear, let's work out a corollary of this. So, and then we'll prove it. So corollary, if z and z prime are two CW approximations for a space X, which is non-empty, then Z is homotopy equivalent to Z prime. So CW approximation, this complicated process of gluing on infinitely many cells, where we made lots and lots of arbitrary choices of generators, it's unique up to homotopy. So our proof is going to be just pick, look at X, put it this way, saying Z is a CW approximation, for X, that's the same as saying Z relative its base point is zero connected CW model for X relative its base point, which is a CW complex. So we are just going to look at this diagram for the identity map from X to X with its two different models, Z prime and Z. I guess I wrote them in that order, whatever. So we're going to get a map H lifting the identity from these two approximations, Z and Z prime. So we can lift the identity map to a map between these, but we can also lift, and I will do this in blue, the identity map going the other way to another map. Let's just call this H prime. And then, because of uniqueness, we can also lift the identity map from X to X using the same model. So, as a map from Z to Z, well, there's a pretty unique way to extend this up to homotopy. I could pick the identity map from Z to Z. That definitely makes this square commute on the nose, so it commutes up to homotopy. So in particular, any other choice, this theorem tells me, has to be homotopic to the identity, and this means the identity on Z is homotopic relative its base point to H prime of H. And doing the same argument the other way, you can see that the identity on Z prime is homotopic relative its base point to H of H prime, and therefore H prime give homotopy equivalences between Z and Z prime. Yeah, which is super duper strong. So we did use the fact that both of these are zero connected and 0 is less than or equal to 0. So that's a pretty important fact in this theorem statement. So let's prove it. Okay, so first we take the models we have from this proof. So we have x mapping via g, which is given to x prime, and we have a map from z prime, z, f to x, and z prime, f prime to x prime, like this. The first thing we will do is replace one of these, I think the right, x prime by its mapping cylinder. Let's just call that, I think, what is he? Hatcher uses w prime, so we'll use w prime for f prime. So we've got, here's a picture of w prime, so I've got z prime mapping along a cylinder to x prime. Hatcher does this additional thing which does little, right, where you take A, so here's the cylinder on A cross I, and since A prime lives in both X and Z, as these little subspaces, you can contract A prime minus I to the part of A prime living in X. So you contract each of those away, and so this mapping cylinder looks only like a mapping cylinder for the additional cells being added on to A prime above degree n prime. And so we're also going to assume new cells only in degrees bigger than n or bigger than n prime, respectively, in z. And z prime. Okay, so what that looks like is I can now replace, so notice that w prime, so we'll decide whether we actually want to retract a prime cross I away, this yellow thing, but w prime already deformation retracts onto x. And we can make it do that relative a, so it's not changing a, which is essentially what this contracting away a prime, relative a prime. So what we've done is we've replaced x prime by w prime, and z prime now includes in w prime as a pair, so we can consider the pair w prime comma z prime. Now the fact that f prime is an isomorphism in degrees bigger than n and an injection degree n means that this pair has trivial homotopy groups in high degrees. So how should we write this? This means that this has pi I w prime z prime equal to 0 for I bigger than n prime. So that's implied by the requirements on f prime's map. So once we have this pair with a lot of non-zero homotopy groups, many zero homotopy groups, we can use the fact that we know n has to be bigger than or equal to n prime. So view the composite map, g of f, as landing in w prime, which is weakly equivalent, or which is homotopy equivalent to x prime. And then we just have to ask ourselves, does this give us, what did the requirements on the homotopy groups being 0 in this high degree tell us about extending maps? So let's scroll down a little bit. So what we know is that we really want to look at the maps of pairs. We're going to look at the map from z, comma a into w prime, comma z prime. The this left-hand thing, this is a CW pair, and the cells in z minus a are all in dimensions bigger than or equal to n. Not equal to, just strictly bigger than n. And n is bigger than or equal to n prime, and that's what we want. So all cell dimensions live up in higher dimensions than n prime, strictly higher dimensions. And so those maps are mapping into groups which are 0. So the compression lemma in particular says, since all of the cells I'm adding on live in dimensions where pi, right, so if k is my cell dimension, pi k of w prime z prime is 0 for all k, which are new cells, or just cells, k cells in z minus a, right? So what we can do by compression lemma is get a map of z landing entirely in z prime, not in w prime. So compression lemma. This is our hypothesis for compression lemma. The conclusion is there exists a map, homotopic rel a to g of f, such that it lands in z prime. So there exists a map, let's call it h, going from z to z prime, with h homotopic to g of f rel a. So this gives the first part of the desired conclusion. And in case it seems a little weird, because it feels like there should be an f prime over here, you have to realize that the way z prime lives inside of w is via f prime. So z prime is really including via f prime into w prime, because w prime then looks like x prime. So this homotopy, if you now collapse w prime, so g of f onto x, ends up looking like the desired homotopy that you'd want. For uniqueness, let's just now assume we've got 2 of them. So assume you've got h1 and h2, both maps from z to z prime as desired. Then we have both that f prime of h1 is homotopic to g of f rel a, and f prime of h2 is homotopic to g of f rel A. So both give maps after composing with f prime, not into z prime, but into w prime. So both give maps, which I'll just call the same thing, h1 and h2, going from z to w prime. But moreover, the homotopies themselves give us maps as well. So let's record that. So I'm going to boost my color. So I've got homotopies h1 and h2 here. Those are homotopies relative A. So they look like, they give maps of their domains to their targets. I'm not sure if I just said that or not. My recording just cut out. So that looks like Z cross I, right? And their target, we look up here, is landing in, let's just annotate right here's H. They land in X prime. So that looks like map X prime. And I have two of these. I have both H1 and I have map H2, and both of these are relative A, so they fix, fixing A cross I. Mapping to X prime, so at all times T, that is just the map G from between the X's. So it's like G restricted to A. At all times. Okay, so these maps also should give us maps of, in fact, W prime. So I have the same argument as above. This gives a map from, well, I've got two of these. So what I'm going to do is glue them together, because I also have G of F, right? So like, yeah, and put it this way, I've got this one over here. I'm doing H1, or H prime. I use superscripts, that's interesting. Let's get rid of those. H1, H2. So I've got H1 on this copy of Z cross I, and then I'm going to have another copy of H2 over here, and this boundary right here is where I'm doing G of F, and over here I'm doing F, the way I think I've done it, F prime of H1, and on this end I'm doing F prime of H2. And so this is just a longer cylinder when I glue it together that's a homotopy between F prime of H1 and F prime of H2. So that big homotopy gives a map from Z cross I relative all of this stuff that fixes A. So and you kind of have to look at the big component of A that looks something like a cylinder like this inside of there. So I'm not going to write it down. Landing in W prime relative Z prime. And this is again just by unwrapping the F prime. Moving to the right, and the same cell argument again, so the target still doesn't have any cells in degrees bigger than or equal to, strictly bigger than n prime, so no, so this is all cells strictly bigger than n, which is bigger than n prime, and this has no homotopy groups. above there. So what this means is this big homotopy between f prime h1 and f prime h2 actually can land inside of z prime. So we get a homotopy between f prime h1 to f prime h2 in z prime. And that now means, well, in z prime means unwind these f primes, and so that's a homotopy of h1 and h2 as desired. So it's really just compression lemma in both cases. So where do we go from here? One thing this model lets us do is compare different cellular models for space. So you should basically think, so consequence of the theorem is that these n connected models are homotopy functorial in the shifting n sense. And so you end up with a diagram like this. So if you have A, which is CW, living inside of X, and X isn't, you can take A and you can produce this zero connected approximation to A, which means the set contains none of A, and it's basically just X, but a CW approximation. So here's a CW column of CW things that we're approximating by. A is also CW, and X isn't. Now, if instead we could make a one-connected approximation, and we'd get this map F1 going back to X, the 1 bigger than or equal to 0 implies that we get a map down, which is unique up to some commuting homotopies. So you have a map between this Z1 model for X and this Z0 model for X that is unique up to homotopy relative A. And you can repeat this. And you keep getting more and more. And I'm just going to also draw the Z infinity case, because the Z infinity case, we said, that's actually equivalent to A. And so you could look at this central column as like filtering the inclusion from A into X. And so what we've done is we've taken A, we've replaced it by this Z infinity CW model for it. Of course, this was CW and this is CW. And then we have all of these new maps to Z0, which is a CW model for X. And so and all of these intervening guys are in fact CW. And those intervening, there's like factorization of the inclusion from A into X into CW replacements is functorial up to homotopy. So the other thing that we should talk about at this point is the Whitehead tower, which we've already constructed, but it's worth talking about explicitly. So this is the tower that we just drew, but I'm just going to factor the point in the map above. So in fact, let me scroll down. So I'm just going to factor, I'm going to let A be the base point of X0 inside of X. So A is kind of trivially CW. And then what I have here is a point, which is weakly equivalent to this Z infinity guy. And all of these are CW by construction. And this tower is called the Whitehead Tower. It is not unique but the maps in it are unique up to homotopy. So if you pick a different model for Z1 or Z2, you can see that you're getting something like close to unique, but there's this 1 degree kind of shift of unicity. So I just want to be careful about that. But let's look at what some of these guys are. So in this tower, Z0 looks like X. Zn, well, the map from the point to Zn is supposed to be n connected. So this is an isomorphism in degrees less than n, and which means that Zn has no homotopy groups in those degrees, and it's supposed to be a surjection in degree n, which means, in fact, it has to be an isomorphism because it's also always going to be an injection, because it's a map being from the trivial group. So what you have is this tower of things where Z0 is, let's switch colors, I don't want these to be maps, these are comments. This is a 0 connected CW space. This one's 1 connected by this assumption here. This one here is 2 connected. This one here is infinity connected, therefore contractible, because it's CW. And so you should think of this as dual to the Postnikov tower, but duality here is kind of a bad term. So let's just be clear. I'm going to draw X in the middle, and we had, I'm off the bottom of my page. Let's just go to another page. Okay, so we had X, and our Postnikov tower, we built this replacement for X. Let's use P1, P2, and they came with unique maps down. So these guys are unique spaces up to homotopy. And maps between them are unique. And P, and it keeps going up, but notice the maps are from X going into it, and the kth level, so pk, let's just go down here, p x to pk is a pi star isomorphism in degrees less than or equal to k. And then, so pk is this truncated thing. And pk, its homotopy groups look like the homotopy groups for x when star is less than or equal to k, and 0 when star is bigger than k. So we start with P1, which is just a k pi 1x 1. It just has homotopy groups in that degree and nothing anywhere else. And then as we keep building up more and more spaces, they contain pi 1 and pi 2, pi 1, pi 2, pi 3, and these maps are required to be isomorphisms in the desired degrees. On the other hand, the Whitehead tower, so this is the Postnikov tower side. Postnikov tower. On the Whitehead side, what we have is a map in from Z0, and Z0's the one that's the most similar to X. And then as we go up the tower, we have a map from Z1, Z2, and so on going up. And ZK is K connected and the map induces an isomorphism in the desired degrees. So k-connected, which means that zk pi star of zk looks like the homotopy groups of x when star is bigger than k, and it looks trivial when star is less than or equal to k, because these maps zk to x is isomorphism on pi star bigger than k. Cool. And those are kind of like the dual pictures of these things. So we will talk a little more about how these things can be constructed, but know that like on both sides these are CW. This is a CW tower, and we constructed the Posnikov tower for when X is CW itself. So we have this kind of two different pictures for how you might approximate a space. One by building, on the right-hand side, by building the homotopy groups from the ground up, and on the left-hand side by slowly forgetting them, or rather building them from like infinity down. So by building via k-connected covers. Let's first check that weak equivalence induces homology and cohomology isomorphisms, which will then tell us that our CW replacements for x and y have the same homology and cohomology. And this means that a lot of theorems that we have assumed the spaces to be CW spaces for, or be homotopy equivalent to a CW space, we can now extend to be to hold for arbitrary spaces by CW approximation. So in order to prove that weak equivalences induce homology and cohomology isomorphisms, we'll just check it for homology and then use universal coefficients. So what we really want to do is look at this map f star in the long exact sequence. However, we just have the map between x and y, and what I need to do is force that to be an inclusion so that I can look at the long exact sequence on pairs. So replace y by a mapping cylinder. So let z be the mapping cylinder for f. Then I know that z deformation retracts onto y, and I have an induced map from f going from x into mf, or maybe I should just call this the inclusion. And now I can look at this pair, mf relative x. And I'm using mf, but I gave it a name, so let's call it z. Z relative x. So I've got x, I've got x glued along f to y, and here's z. And I'm looking at z relative this copy of x. So the long exact sequences in homotopy groups those imply that the space pi star of z x is trivial. All of these homotopy groups are trivial, like in all degrees. And the long exact sequences in homology and cohomology relate the maps we like to care about, so just focusing on homology, we have like the nth homology of X. I'll suppress G. I've got F star mapping to the nth homology of Z, which is isomorphic to the nth homology of Y, and then mapping to the pair. And then mapping down. And so what we'd like to know is that the triviality of pi star implies triviality of homology and dually cohomology. So the claim that I stated is we have a pair with trivial homotopy groups for the pair for all degrees, and we claim that its homology and cohomology of the pair is also trivial for all n. I want to point out, just because this pair has trivial homotopy groups in all degrees does not mean it is contractible. We've only proved that for spaces which have the homotopy type of a CW complex, and X and Z both don't have to have the homotopy type of a CW complex. We just have a nice inclusion from X to Z, which makes it a pair. It's a closed inclusion. So, yeah, so I'm not saying that the pair Z comma X is like a homotopy equivalent to a point somehow. I'm saying that it does have trivial homology and cohomology and relative homotopy groups. But it's not a CW complex. So, well, let's prove this. Proving something about homology, so just like assume we've got some chain. So we've got a finite chain of, let's call alpha I, AI for my coefficients, I, in Cn, let's say it's a cycle. Yeah. Say this is a cycle in chains on Z, comma X with coefficient group G, representing some element in, some non-zero element in cohomology. Then we want to show that it actually is a zero element, so what we do is we pick, oh, I made alpha on both sides of this equation. Let's, here, I'm fine with the coefficients being A, but let's make these sigma for simplices. And let's just fix what those simplices are. Each sigma I gives me a map from some delta n into Z relative X. Let's just say into Z. So what we could do is use all of these, build a simplicial complex that represents the whole cycle. So what I'll do is let K be a big gluing construction over I on delta n's, where they are glued together along their face maps when different simplices have take the same value on a face. So because it's a simplex, it's because this is a cycle, I've got, maybe all sorts of, I'm drawing it in one dimension, all sorts of guys. So here's like sigma 1, sigma 2, etc., sigma n, right? And it has to be a cycle, and now K looks like this, right? And maybe if what I'm drawing is the image in X, cycle in Z, then K is going to look like, and then because 4 of these guys have the same points, it's going to identify like all of those edges together, all of those faces together. And so what you can get is alpha basically gives you the data of a new map from K, let's just call this alpha, K to Z, which is doing AI, sigma I on each little piece. And so it's, or it's doing sigma I on each little piece, and then the AIs give us coefficients. So, yeah, I've got this big. Okay, so what have I forgotten? Oh, this is only needs to be a cycle in Z comma relative X, which means that this cycle could have kind of guys hanging off it that then these guys both live in X. So it only has to be a cycle relative X, which is fine. So, but both of those guys are going to land in X. That's a sort of picture. I have to change my picture. It's just, here's what K kind of looks like. So it has to be a cycle landing in X. Landing in Z minus X. Yeah, so boundary alpha, this is a chain in X because we're a relative group. That's what I want to say. So what I want to do is peel off the components of K that land in X and map them in relatively. So what I'll do is let L be parts of K, the faces of K, that end up in boundary alpha, so that don't kind of cancel each other out. And then what we actually have is map K relative L to Z relative X. And L and K are both compact, because they're a union of a bunch of simplices. So this is fantastic because K is entirely made up of, K and L is a CW complex. So this left-hand thing, KL, is a CW complex, and pi star of ZX is trivial always. So by compression lemma, alpha is homotopic to a new, let's just call it alpha bar, mapping from K into X. And so K entirely lands inside of X. But if K alpha is homotopic and this homotopy is happening relative L, and in the simplicial homology world, or singular homology world, that means the chain represented by alpha is equal to the chain represented by alpha bar, but since the chain represented by alpha bar lands in X, it's 0 in, let's just get rid of those brackets, it's just 0 in the nth homology of Z relative X with coefficients in our group G. And so the guy we started with was arbitrary. He has to land in X by compression. Therefore, they all do. So as a consequence, we get that weak equivalence takes yeah, if two spaces are weakly equivalent, then they have the same. That weak equivalence induces an homology and cohomology isomorphism. Cohomology follows directly from universal coefficient theorem. So two last results before I lose my voice today. So the first is, let's say, a Kuna theorem. Recall Kuna theorem was telling us about isomorphisms of cohomology of products with the tensor products of cohomology. So it's something that looks like cohomology of x cross y with coefficients in some commutative ring R is isomorphic to the cohomology of x. That cohomology ring tensor over R with the cohomology ring of y. And we knew this was true when x and y are CW complexes, and they have finitely generated homology, cohomology in and both x and y have finitely generated cohomology in each degree, and cohomology of y in each degree is free. And I think we maybe even in our proof we got this if free is replaced by a projective. But the new thing we can do is we can just totally eliminate a CW complex part of this, because spaces have the same, can always be replaced by CW approximations, which are weakly equivalent and which have the same cohomology groups and cohomology rings. So our conclusion here is that by taking our old proof, we can get a new proof just for x and y spaces with these restrictions on their cohomology, provided we first replace x and y by say x prime and y prime, which are CW complex replacements, since their cohomology is going to be finitely generated in this way, and it won't, since the cohomology groups won't be changed degree-wise, the assumptions don't change. So we get the same conclusion. So that's a good example of how useful CW approximation can be. And I also talked about this when we talked about Whitehead's theorem, just how useful CW approximation can be. The final thing I want to get is just to use the compression lemma for one more thing, because we've used it for like 5 things in a row. So proposition is that if f x to y is a weak equivalence, then for all spaces z, the homotopy classes of maps from z into x and from z into y, well, there's a map between those which is induced by f, composition with f, so f of. This is a bijection. Of homotopy classes of maps. And the only requirement I need is Z has to be a CW complex. So let's prove that as well. So the first thing we do is we replace y by its mapping cylinder so that f is actually an inclusion. So instead of looking at f, replace fx to y by, I'm just going to call it mf, by the homotopy equivalent version of x into mf. So here's my mapping cylinder. And I'm just going to call this inclusion f. So by assumption, I now actually have a closed inclusion of x into mf. So I can assume this map is a closed inclusion as well. So as a result, my homotopy groups, so the relative homotopy groups of mf relative x, and let's pick a base point in x, these are 0. These are 0 for all n. And so now when we're mapping from any CW complex, our, we have any map, so any map from z into mf. Yeah. So if we have map z to y in the target, let's just call this A. So A lives there. We can think of it as a map from z to mf, right? That has to extend. So we have a map from z to mf. So we end up with a map from z relative its base point. Let's just call that z naught. To mf relative x. And now the compression lemma tells us ZCW implies A is homotopic to this new map, A prime, which takes Z into X inside of MF. So, as considered, both of these as maps into MF, they're homotopic. And this means that I get this new map A prime, and up to homotopy, A prime is being mapped onto A. And so that tells me that F, the induced map, I should just call this F star. I'm going to change that in the theorem statement. F lower star is surjective. And now, to show it's injective, we just need to pull back a homotopy. So if, let's scroll up a little bit. So if, did we do that? If B and B prime both map, are maps from Z to X, such that F of B is homotopic to F of B prime as maps from Z to Y, which we can replace by MF. Then what we can do is just pick a witness for this homotopy. And so now that map H is a map from Z cross I into MF. And we can take that relative base point, C0 cross 0, let's say. I don't love how I wrote that. Let's just give myself some extra space. Into MF relative X, and again, the right-hand side has no homotopy groups. The relative homotopy groups are trivial, so this has to land in X. including into there. And this commutes up to homotopy. So H is homotopic to this H prime. And H prime goes from Z cross I into X, and H prime now witnesses the homotopy between B and B prime. And that ends our proof. Just 2 compression lemmas. And that's it for today.